Good morning and good evening, everyone. I'm Jingjong Zhang, a researcher from Recon AIP. Today, I'm going to host the 10th TrustML Young Scientist Seminar. Before that, allow me to briefly introduce Recon AIP to our valuable guest, Jumi. The full name of Recon AIP is the Recon Center for Advanced Intelligence Project. AIP was founded in 2016 as the research center for the MAX AIP project. AIP Center conducts Japan's leading AI research, which is headed by Professor Sugiyama. AIP aims to enhance the AI's fundamental technology and its real-world application. We encourage the collaboration with various researchers and engineers in related fields. We would be very grateful if you could visit us in our Nihonbashi office in Tokyo in near future. Zhongmin Yun is a PhD student in Jiazhou Graduate School of Artificial Intelligence at Korea Advanced Institute of Science and Technology, KAST, under the supervision of Professor Zhu Ho Li. Since August 2020, he got his bachelor and master degree in the Department of Electrical Engineering at KAST at 2015 and 2017, respectively. His research interest led to generated modeling, adversarial robustness, and stochastic process. Hi, Jumi. You can get started. You're talking right now.
Okay, thank you very much for introduction. My name is Zhongmin Yoon, a PhD student at KAIST introduced. And let's get started for our presentation, and don't hesitate to ask questions if you're very interested. And my work is on the adversarial purification on score-based generative models, which is on the working on some adversarial robustness work on machine learning project. I mean, this is the joint work with Sungju Hwang and Zhu Ho Li, which are the professors in my university, and this is represented in AIP Japan seminar. Yeah. And the background, I'll introduce the background. The first one is on which you are very familiar with adversarial training and pre-processing adversarial purification works. And the second is the recently featured generative models, and which are achieving the state-of-the-art performance, which is named score-based generative models. And then I'll introduce a method. Our main method is that purifies the adversarially attacked images with score-based generative models, and how these purified models can be attacked and how well it can be defended. So adversarial attack, I'm gonna just briefly introduce this concept because you are all familiar with. The adversarial overparameter nonlinear models, which are also called the neural networks, are vulnerable to some data which are perceptually the same with other data, which are all well predicted. We know that we already call this as adversarial examples. For example, the left side data, which they are classified as panda by some networks of the ImageNet network. Image classifier network. However, even when the very small amount of adversarial attack is given, then even though that we know that with perceptually know that it is a panda, it is still a panda, but the neural network fails to classify the network as it is classifying this as gibbons, as very high confidence. And to remedy these adversarial attacks, we use some worst case risk minimization problem. Having some robust model is equivalent to having some correct prediction at the worst case examples, even though that the worst case example is given. Then the worst case risk minimization problem is given as the optimization problem below. This is to minimize the neural net, minimize the parameters with respect to the maximal loss with respect to the threat model. The threat model is defined as the set of possible attack points from X, and the G phi X objective is the objective classifier model. However, this getting the worst point at the threat model is generally infeasible to find the worst case attack X prime at BX. So we perform the common way to resolve this is adversarial training. This is given by approximating the inner maximization loop. And this is performed by modifying the worst case minimization problem at the red side into the certain class of expectation over the certain class of algorithms that find the vulnerable point as the blue side. And this some common solution of the AX is the projected gradient descent, even though there are more methods called the FGSM or the recently proposed ODS method. The projected gradient method is among the existing algorithms within AX, the projected gradient descent is mostly used for finding gradient-based local worst-case examples. This is simple and largely performed in 2 steps. The first step is to add random noise within the threat model, and to choose the starting point. And the second step is to find the direction of each pixel that maximizes the loss function to find adversary examples. To generate a robust model using the PGD attack, and then given this generated adversary example, we perform the loss minimization gradient descent. Then adversary training by using this PGD adversary examples improves robust accuracy by avoiding the label leaking effect caused by one-step gradient descent, such as FGSM. There are some way of improving this random noise, giving random noise within threat model, such as ODS or output diversifying sampling. But this is out of scope in our presentation, and I'm going to skip this. And however, we know that this kind of adversary training our adversary machine learning community shares some awareness considered in some seminar works. And we work with some adversary training, then as the model becomes robustified, which means that the robust accuracy becomes higher, they can achieve low performance compared to its adversary vulnerable counterparts. Adversary vulnerable counterparts means that some models that are very weak with respect to the adversary attack models, but very getting the high performance in some standard accuracy. This is a well-known benchmark from Francis Cross, and the standard accuracy of widely used ResNet or whiteness network of cipher10 data using batch normalization goes to 95 to 96% standard accuracy. But figure 1 shows that the standard accuracy is not enough to reach 92%. Unless extra training data are used for when we give some training for adversary training when we use for attack with L infinite noise of 8 pixel levels. And to solve this, this becomes the caveat of the adversary training method. So first, the caveat of the adversary training method is this works well on known attacks when the algorithm AX is given. But if the AX is not given, this can be weak on unknown attacks. For example, even though some attacks are performed well in L infinite noise, when the sparse noise in other names, some L0 noise is given, that this does not work in L0 noise or something like this. And the second one is the adversary training network shows weak standard accuracy, as we showed in the previous slide. Each can be resolved respectively by the first one can be resolved by proposing certifiably robust models, and this is verified to work for every possible attack under certain given conditions. And the second one, weak standard accuracies, solved by keeping the original network and plug in other transformations for method for input data. This enables to use the high quality original network, which is not weakened by doing some adversarial training. And this defense by preprocessing is done by this way. And first, keep the original network and use preprocessor network F theta. Theta is it can be either parametric or non-parametric. So F theta given with either a neural network or aware corrective function. Then we modify the adversarial training problem as the red side is the adversarial training problem and the blue side is the defense by preprocessing. And by doing the defense by preprocessing, we can leave some high quality flash file network. Then adversarial purification is a type of this defense by preprocessing that use generative model as a preprocessor and restores clean data from attacked ones. So far, this was the introduction on the adversarial training, which we are familiar with. And this part is a rather non-familiar part, which is generative model part. And the score-based generative model, or which we call diffusion model in recent terms, is a generative model which uses continuous dictionary of expected noise, which are also named scores, with respect to various perturbation levels of the input data. For example, we first perturb the data, or the left side dog data, into the and gradually add noises to this dog data. And lastly, we are not able to distinguish this perturbed dog data into the random noise data. And given the random noise data, we are in the next page we recover the data distribution from this random noise distribution given by the score function. And given this SDE, forward SDE and reverse SDE, given this reverse SDE, and when the score function is well estimated, then this is enabled. There are mostly three components of the score-based generative models. The first is which data to train. We take which data to train, and we take pair as perturbed data and perturbation noise, where the perturbation level monotonically increases and make the data from non-perturbed to the data which is indistinguishable to tractable random noise. And the second part is how to train the SGM. We use the neural network S theta, whose input distribution D is the dimension of the image distribution, and the output dimension D is same as the input dimension. Then the third one is how to sample from this score-based model. Once the noise is estimated, we can denoise the perturbed data sequentially and gradually from the more perturbed one to less perturbed one, and lastly, not perturbed at one. Then we are going to more introduce the how to train the SGMs. The score model, gradient, log gradient of PX is tend to approximate the true score function when run correctly. And the denoising score matching is a way to train this the score function are not the marginal score function, but the conditional score function for the noisy data. The idea is learning all the dictionaries of the score function of the perturbed data. This means that given the noise level, and noise level becomes a component of dictionary, and we learn the corresponding part of the corresponding score function with the noise level sigma. Let the conditional noise distribution be Q sigma of x tilde given x, where the x tilde is a perturbed data and x is a non-perturbed data. Then the DSM objective becomes expectation of the pair of x and x tilde, and the gap and the norm between the gap between the conditional score function S theta given X and parameterized by X and the noise level sigma. And the conditional score function X grad X log Q sigma X tilde given X is minimized. And the DSM objective is equivalent to the original score matching objective, which minimizes the marginal score instead of the conditional score in terms of adding a constant. This constant is also called for the conditional feature information. And the last and most important part is the how to sample from a score-based generative model. We introduced unified sampling rhythm here, which includes the already known the ancestor sampler as the solver language sampler, which are all the samplers of the mainstream work of the diffusion model. Given that the current sample X sigma is perturbed with noise level sigma, then the next sample with noise sigma sigma prime, which is smaller than sigma, is obtained by the formula below. The X hat sigma prime is given as the linear combination of sigma X sigma and the score function estimator S zeta and the random noise Z. And given that given that A1 and A2 and A3 are given as a good choice, then it is a high generation performance, but we skip the details of the solvers beyond the scope of this our interest. The later seminar will be I guess that a later sigma will be dealt with the diffusion model, and when this will be addressed later. Yes, and this is an example of the sampling from the score-based generative model. The upper blue side is a forward trajectory from the noiseless blue data at t equals 0 to the noisy data at t equals capital T. And when the noisy capital and noise distribution at capital T at the red right side data is given, then by using this bottom row drift function, and the drift function propagates the noisy data into the noisy data into the suggested distributions, and as the time goes to a large T to 0, and the drifting term becomes more concentrated to the original distribution from the random noise distribution, and more focused on the original data distribution. And lastly, at t equals 0, the reverse trajectory recovers the original data distribution except for some out of distribution data. And so far, I introduced the score-based generative model, which is the key ingredients of the adversary purification with some score-based generative model. And I'm gonna introduce what is adversary purification, which is an alternative method to adversarial training for adversary training. And adversary purification, which I briefly introduced at above slide, stands for the class of methods that use the generative models as the preprocessor. We call this as prefier and leave the classifier to be original ones. There are some advantages of adversary purification. The first is the purification is unaware of the attack method. And the second is we can utilize the good performance of the original classifier network. Here we see how adversary purification works. The above row of the figure is stands for the adversarially attacked images, and the below, bottom row stands for the purified images. And because the adversarially attacked images are not perceptually distinguishable from the original image, then also is the purified image from the adversarially attacked image. And the existing work on the adversary purification are directly input the attack data and purify these by using various kinds of generative models like denoising autoencoders and energy-based models and flow-based model, generative adversarial networks. And the example is the figure below is one given from some work in the energy-based models. And On the right side, we first get the adversary attack image and update this by using the long-domain dynamics, which inputs the original here original image and add this up to the score and add some noise and get the next image. And by running this long-domain dynamics over about 1,000 times, and the purified image is given, and from the purified image is when this is normalized, and then classifier is given, then they can earn the input performance, robust performance, and robustness performance. Then the key idea compared to this existing work is an adversary attack data consists of two components. First is the signal, and the second is attack. The score-based generative model is specialized in removing a large amount of noise and leaving signal. We should be aware that the score-based removing a large amount of noise is the specification of score-based model. And if the noise level is much greater than the attack level, then noise plus attack data is indistinguishable to noise, because the attack is usually very small and small, not to be distinguishable, or not making the attack data not distinguishable to the original data. Then from this insight, our algorithm starts from injecting some random Gaussian noise into the original image to screen out the adversary attack. Here, from the left side is the attacked image, and we inject noise of level sigma. We use some sigma equals 0.25 in the Cypherton data, which is commonly used to pairwise maximal pairwise distance between the training or validation data. And we get the score function, which is the estimated injected noise every step, and perform deterministic attack update. At the time of my research, the deterministic update is done heuristically already by choosing deterministic to choosing from deterministic and some stochastic update. But it is known for some seminal work for called DDIM at the field of the generative score-based generative model, that the deterministic update is very effective for when we should hold some small number of updates, and this was heuristically already found in our work. And so and after holding some deterministic updates, and we stop the update if the score function is small enough, meaning that the image is purified enough. And then if it is stopped, and we pass the image through the classifier. This is the algorithm, and as you see that this is the first we perform the deterministic update, and we get the level of the update, and if the score level is small, and we stop the update, and run the classifier network. There are some issues on attacking adversary purification models. Basically, adversary purification models are hard to attack because of the following aspects. First is the obfuscated gradient. Since noise is added, it is hard or impossible to estimate gradient. And second is a long loop. The long purification loop causes the gradient estimation harder and make it harder to save all the trajectories. Sometimes the long purification loop causes the network to have gradient vanishing or gradient exploding effect. And some tricks that approximate gradient for some cases, those cases may attack the adversary purification models. The seminal work for Asalier, which is called the circumventing branches with obfuscated gradient, proposes some attack methods that breaks all the existing method, including early adversary perturbation method or other transformational method, except for the known adversary training methods. The first is the BPDA attack. BPDA attack assumed some non-differentiable part of the network, for example, some non-linear, non-differentiable transformation, or some, in our case, the noises, as then approximate the gradient of this part to be identity, and leaving this part to be identity, then the non-differentiable, previously non-differentiable network becomes differentiable. Then by making this differentiable, we can make some gradient like the PGD-like attack, the PGD-like attack for the stochastic network. Then the second, the EOT attack, is helpful for attacking some randomized classifier. Since our adversary purification networks randomized classifier, this EOT attack is useful. Consider multiple stochastic transformations by taking expectations of all over transformations. And these BPDA plus EOT attack breaks almost all the text here, like here. The above block is all the transformation and adversary purification works, and the below block is for the adversary training network. And this work showed that the adversary training is robust in a BPDA plus EOT attack, because it doesn't work for BPDA, and both BPDA and EOT is not for adversary training ones. But however, for the adversary purification ones, then BPDA plus EOT attack is useful. That makes the robust accuracy almost 0%. And even though this is the defense GAN paper, which used the GAN network for GAN network, but it is that data set is MNIST, so this accuracy is quite low one. I cannot go next. Okay, I went to the next slide. And it is well known that the number of PGD attacks largely affects the performance of the network. And I verified the performance of the attacks within the BPDA attacks. And as the number of BPDA attacks goes from 40 to 100, the performance degrades only by 0.3%. On the contrary, the number of EOT iterations affects largely to the difficulty of the purification. This is because the number of EOT becomes greater. This fully reflects the stochasticity of the network and weakens the effect of the randomized classifier. However, as this number of EOT shows, then when the number of EOT becomes larger than 10 or 30, and this is likely to be somehow converge to about some 67% accuracy in the CIFAR-10 data set. And taking EOT in 50 times and BPD as 40 times takes more than 1 week, and we stopped the number of EOT as the 50 times and did not run more than this. And when we check the performances when the purification steps gets larger, the left image shows that how the T-SNE diagram of the attack data and purified data. And suppose that the image is the MNIST image, and the MNIST image starts with some adversarially attacked one to some purified one. And when this shows here, the adversary attacked one is very far from the cluster of the true label data. And however, as it is purified, then this approaches to the true data very fast way. It only takes on 2 to 3 steps for MNIST data. And the right side is the x-axis of the right side is the number of purification steps, and the y-axis the performance in CIFAR-10 dataset. And we showed that in about 10 times of the purification steps, then this approaches to the maximal performance we can achieve. Yes, then we show the full result of our experiments for various kinds of attacks, and we describe the attack. The first one is the preprocessor blind attack, which the attackers are not see the preprocessor, and we take the classifier PGD attack, which is the same as the original PGD attack, which only attacks the classifier and leaves the ignores the pre-fire network. This is considered as transfer-based black box attack because our purification network is considered as the black box. And the second one is the strong adaptive attack, which is BPDA plus DOT attack, which we described above. And the third attack is common corruption, which is the perceptual attack, which consists of 15 different kinds of perceptual perturbation. The figure below, figure 5 describes the common corruption. The above the top row is the common corruption images, and the bottom row is the purified image. And we show that for some domains, the corrupted images are purified so much, such as this, some noise cases or some glass cases. But for other domains, they are not purified much because it's obvious because our purification method is specialized in Gaussian noise cases. And first, the preprocessed blind attacks, the result, the performance gain is very strong because it is obvious because when the preprocessed blind attack is given, then the purifier network is not prevented to purify all the information, and this is very weak attack, and all the previous adversary purification methods does it very well. And when we compare this to the transfer-based adversary training method, which from Madri or Zhang, and the robust accuracy is more than 70%, and for ours it is more than 80%. But however, this is not a fair comparable because the ways are different. And we should know that this attack is comparably easy. And when we deal with some stochastic or some when we can use the BPDA plus DOT attack, we should not do this preprocessed blind attack and deal with some BPDA attack. And this is the result for the BPDA plus DOT attack. And as we use some better networks compared to the previous work and previous adversary purification work, and we achieved some better performance compared to these existing works. And even though the different attack given to existing adversary training method, because they use PGD attack to the adversary training method and BPDA plus DOT attack to these adversary purification works, and they are at least comparable. And the final result is up to the common corruption attacks. And the first row is our ADP result, and the second block is the second block is the result for the adversary training method, and third block is the perceptual robustness works. And of course, the perceptual robustness works shows the best performance, but our adversary purification work works well for both high denoising and no denoising cases, and it shows a slightly better performance than the adversary training method because our work is specialized for purifying some noise and digital corruptions, and some common corruption includes some noise and digital corruption, and these are fully purified up to according to our approach. So far, we showed the experimental result, and now we are going to provide some insights of investigating the adversary purification. So far, we have observed the following aspects of adversarial purification, such that adversarial purification is same as the randomized classifier with generative model. And the work by Cohen in ICML 2019 showed that randomized classifier achieved certified robustness with respect to L2 threat model. And a classifier is certifiably robust with an area including X if the classifier always predicts a constant label inside the area. And the result doesn't change whatever attack is given in the same area. Then the adversary purification guarantee is shown empirically shown to guarantee the certified robustness as in a similar rate of the randomized classifier of the Cohen's work. Yes. Then I'm gonna provide a conclusion And the adversary purification is the pre-processing based robust machine learning method and had been enabled by recent progresses in generative models. And score-based generative model is a good block for Free Fire. I'm gonna shed light on the further directions of this kind of work. And first, I used NCS and version 2, which is proposed in 2020, each over 2 years. And recently proposed score-based generative model achieved the state-of-the-art performance of the unconditional image generation, such as some DDPM or some score SDE. And I guess using this more recent work will use a far better performance than which I did here. And some more analysis on adversarial purification methods and certified randomized smoothing classifier will vastly help the analysis of stochastic some robust machine learning methods. Yes. And thank you for, this is the end of my presentation, and thank you for the attention. And if you have questions, and don't hesitate to ask questions. There is a question, then any insights on attacking score-based generative model and improving its robustness? Well, I think that attacking score-based generative model is quite difficult and it is my personal guess that the score-based generative model provides every single conditional score function for every noise level, and this will be some tight bound. It is just my insight, and adversary purification with score-based generative model with optimized score-based generative model will be tight bound of the L2 or certified randomized smoothing classifier, and I think it is quite robust. And how to attack score-based model when there I think it is very difficult to attack score-based model. I don't have any idea of attacking score-based generative model.
Yes, basically my thinking is about we have a noisy model, then we have a noisy model, then we add some Gaussian noise gradually, right, to get some purified image, right? We have a noisy image, then get a purified image. Then during the process we can get add the noise gradually, So yeah, you mean that by adding noise gradually we cannot attack the model, right?
Right.
Because of the accumulating the noise. So it's kind of like it depends on the component we want to change. Now we only allowed to change the input,
right,
in the noisy input. can we allow to change some of the noise we added? Is that possible? I guess it's no, right?
What if we don't use the noise as the L2 noise or something like some word noise? And this will be some good insight because some sparse noise, something like sparse noise. The sparse noise, I think that this score-based model-based work is some vulnerable to some sparse noise because
sparse noise.
Something like sparse noise.
I see.
And however, I empirically showed that for common corruption, this is a common corruption result, and the noise corruption in the common corruption benchmark, it provides some short impulse noise, includes an impulse noise, and impulse noise is the kind of sparse noise. And I empirically showed that our method using the score-based model also recovers good original image from this sparse noise adversarial input. Well, this is just empirical. This cannot be showed by up to the best of our knowledge. This cannot be showed by some certified randomized smoothing classifier perspective.
Yes. Yes, it seems like the indirectly adding the noise into the same model inherently increase some robustness, right? You mean like the score-based generating model inherently have some robustness?
Right. This is what I mean.
Yeah. I saw from the result, it seems so. Yeah, it's like it seems we can get this conclusion. Yeah. By indirectly adding the noise. I see.
Okay, thank you very much.
Thank you very much for your answer. Hey, audience, if you have any questions, please show up to discuss it. Basically, I have a question. For example, that another question. The diffusion model actually is an indirectly processed, right? So when we want to think about the deployment, sometimes this interaction process is very time consuming.
Right.
So that would be not that really fast. We have to purify the noisy image first, then get the clean image, then feed to the classifier. So any insight for accelerating the purification process?
This has I have some insights on purification process, but it has constant process. And this is because that when we shorten the purification process by using the efficient sampler, using an efficient sampler is a good way to for fast purification. But using when we use the fast purification, and the effect that makes the diffusion model robust becomes weakened, because the fast sampler usually use less noise than the more longer sampler, and the effect of randomizing noise is first weakened. And as I said before, when the purification step becomes shorter, then the gradient of obfuscation effects, such as the gradient vanishing or gradient exploding, gets weaker too. Then yes, there are so many ways to shorten the purification process, but this also weakens the robustness. This is my insight.
I see. This seems there is a trade-off, right?
Right.
Trade-off between the process and the purifying the adversarial noise. So it's kind of like a no free lunch. If we want to purify the adversarial noise, we have to take a longer time to do that.
I think so.
I see. That's indeed a very good insight. Yeah. Great. Yeah. Since there are no further questions coming up, let's sincerely welcome and appreciate Juni for his great talk. Yeah. Now the next speaker, Sihang, is coming. Hi, Sihang.
Hi.
Hi, great to see you. Yeah, let me introduce Sihang. Sihang is an assistant professor of School of Computer Science and Engineering at the University of California, Santa Cruz. His research interests lie at the intersection of computer vision and machine learning with the goal of building robust, explainable AI systems. Sihang received his PhD degree from Johns Hopkins University, was awarded with the Facebook PhD fellowship. Sihang served as an area chair of ICCV, ECCV, ICLR, and NeurIPS. For more information, you can visit his personal website, cihangxie.github.io. Hi, Sihang. We sincerely welcome you. You can start your talk now.
Okay. So first, thanks for inviting me for talk here. The topic I'm going to introduce today is towards robust representation learning and beyond. So first, there is no doubt that deep learning will lead some huge revolutions in AI. For example, with deep learning, we can now beat the best Go player in the world. And also with deep learning, our robot can solve the Rubik cube problem. And again, with deep learning, you can see from this Tesla auto-driving system, it works pretty reliably, at least from this demo, works pretty reliably for the most time. And all this successful story basically motivate us to think, okay, our current AI systems are really as intelligent as we think. Well, I think for this seminar, the audience of this seminar probably already know the answer. Of course, it's no. And actually, deep learning can be pretty easily fooled. For this real image, like our image from the real world, you send it to the current computer vision system. But it can, of course, like say very high confidence to say this is a king penguin, and it's aligned with our human perception. But if you get some small noise to this king penguin image and resend it to the current AI system, this system will run it, take it as our chihuahua. So basically, for this such sample, we call it as adversary examples, and I'm pretty sure most of you guys already know the background here. And for the existence of adversary examples, basically it reveals there is a huge discrepancy between human vision and the machine vision. Because for human vision, we definitely know and we're pretty sure this is a king penguin, while for the computer vision, it just think, okay, very high confidence think this is a chihuahua. So by focusing on this problem, my talk will be can be divided into two parts. The first part, I will talk about how can we build a robust representation learning to better recognize such adversary examples or even be some out of distribution samples. In the second part, I will reveal that learning with adversary examples, we call it as robust learning, actually can improve their model. So for the first part, towards robust representation learning, the basic goal is that, say, we get the adversary inputs and we send to the network, and we wish the network can already, like, say, learn some robust representations. That means, given this adversary examples, network can still extract their features correctly, and then the final result should be correct to say this is a king penguin. And my special take on this part, building robust representation, is by designing robust neural architectures. And basically, this part involves three works. The first work that I'm going to talk about is feature denoising for improving adversary robustness. And this is pretty old work, CPX 19, 2 years ago, right? But I still want to talk about this as this is the first work that is establishing me with the evidence that we really can find some robust architectures to get better robustness. And the first look at the motivation here. If we just look at the adversary examples and the clean images out of the pixel space, our human eyes can hardly tell there are any differences, right? Like look at this column, this row here, and this row here. Basically, our human eyes think they're basically the same. But if we look at this images at the feature space, here the feature space refers to the output of an intermediate neural, like an intermediate layer or conv layer, and visualize it is output. And we can see that compared to the clean images, the feature map of adversary images, they appears much more noisy. For example, you can see the noise on the background here, some noise on the boundary here, and a lot of noise on the background here, right? So given this observation, we take a very simple step to make better robust network. We basically say, okay, we should denoise these feature maps. So for denoising feature maps, what we consider is just some traditional image denoising operations. But instead of, say, executing them out of the pixel space, we put these image denoisers out of the feature space to denoise these feature maps. And we just consider some more basic filters like bilateral filters, median filters, mean filters, and some non-local means. And directly insert these filters out of the intermediate layers of the network can kind of degrade network performance. It is mainly because that denoising operation may lose information. Just imagine that you add a median filter, apply it to your image or to your feature map. You can see that this basically will remove a lot of usage, a lot of information, right? Because median filter just let the median value pass through to be the output, while just throughout all other informations. So to kind of prevent this information loss, we add a residual connection here. You can see here, residual connection, basically to balance the trade-off between this path of removing the noise and this path of retaining the original signal. And we add a one-by-one convolution here. Basically, it serves as a way to automatically learn the balance between these two paths. And for the training technique, we basically consider the adversarial training. The key idea of adversarial training is introduced by Ian Goodfellow in 2014. Basically, just say, we get adversarial images, then we just send these adversarial images into the neural network for training. And you can see here, the key difference between the adversarial training and the vanilla or standard training here is that the input gets changed. Here we just exclusively use adversarial images for training. And for the robustness evaluation, basically we just consider two very standard situations. The first is defending against a white box attack. That means the attacker can access to the network and can directly manipulate the output, use the gradient information of the network to directly manipulate the pixel space, the inputs. So this is generally considered as a very harsh way to, or the worst case scenario to evaluate a model. And also we consider the blind attacks, which is a more real-world scenario. That means instead of directly manipulate your network, the attacker can only access to the substituted network to generate adversarial images. And because adversarial images kind of have the transfer property, that means the adversarial example generated from one network can also attack, in certain chance, successfully attack the other networks. So attacker here just say use a substitute network and do the white box here, generate the adversary examples, and send this adversary example to our target to fool the system. And first look at the white box setting. Here's the results. The x-axis refers to the number of attack iteration. Basically, more attack iterations means you are applying a stronger attacker here. The y-axis is the top one accuracy on ImageNet. And the red curve is a baseline model. Basically, that is the ResNet 152 plus adversary training. And you can see for this red curve, the evaluation curve is asymptotic. That means empirically, even with say the 2,000 step attacker, we can still have a very reliable results to defending against this strong attacker. And by building upon this baseline model, we add denoising layers, which is the model shown in this yellow curve. You can see compared to this red curve, this yellow curve might get significant better performance. And this can indicate that feature denoising can give us additional benefits for defending against adversarial attacks. And we also pin down to different denoising operations. We do the experiments with 3x3 mean filter, 3x3 median filter, and bilateral filter, and the non-local filters. You can see compared to this baseline model, the red curve here, all denoising operations basically can give you better performance. And next, we just do the black box setting. And to make the evaluation easier, we just send our model to our online competition. Basically, we just submit our defense model, and there are 48 teams, unknown teams. They just submit their attackers. So we just compete with each other to see whether our model can successfully classify the adversary examples generated by these 48 teams. And here are the results. You can see that the blue bar is our results, and we're the first place. We basically can beat the second place by around 10%. And also, it's worth noting that starting from the third place, all the answers get below than 10%, which can kind of demonstrate this task is pretty non-trivial. And lastly, I would like to show our visualization of this feature denoising. You can see that for the feature map, before the denoising, you can see there are still some noise here, right? And after this denoising operations, you can see most of the response just focus on this semantically meaningful area, and a lot of noise just get suppressed. So this can kind of qualitatively evident that our denoising operations are indeed denoise the feature maps for getting better results. And the next work I want to introduce along this direction is called smooth adversary training. So basically, when we design the neural network, by default, the actuation function that we choose is called the ReLU, right? And for the ReLU, it of course enjoy a lot of benefits. For example, they are easy to implement. They can do the in-place operations, right, to reduce their memory. And also the gradient is pretty easy and fast to, you don't even to compute the gradient, right? Gradient is just 0 or 1. But if you took a closer look at the ReLU, like say the forward is like this, for negativity input, the output is 0. For positive input, the output is just the input itself, right? But if you just take a look at it is backward pass, you'll find that, like say negative inputs, the gradient is 0, positive inputs, the gradient is 1, and here is an abrupt change, right, at the original point. And in later ablations, we just find that this abrupt change in the gradient significantly weakens the robust learning. And here are our experiments. So before we do those applications, we first just give you guys a brief overview of how ReLU get used in standard adversary training. First, we have the attacker. We attack the network, right? And we get the adversary images. And here we use ReLU, right? To generate those adversary images. Then we have these adversary images. We should send back to the network for adversary training, right? And to update the network to calculate those gradient to update network parameters, we again use ReLU, like say the ReLU is used here, right? So basically ReLU is used 2 times in adversary training. And to apply the effects of this abrupt change, what we do is that with ReLU, we just replace its backward path with the soft plus, the gradient of soft plus. Okay, so forward is ReLU, backward is the gradient of soft plus. That can kind of give us our smooth gradient, right? And this change, do remember that forward we always keep using ReLU. That means we use the max between 0 and the input to get the forward path. Okay, just in the backward path we change the gradient. And by using this new function, we can see that first we just do these ablations on the attack. The attacker assesses the network to generate adversary examples. And here, rather than using original ReLU, we here use the ReLU with smooth gradient, right? So you can see here we use a smooth gradient to generate the adversary images. And then by getting this adversary images, we send to the network. Here we just using the original ReLU. The only purpose here is that we want to benchmark how the smooth gradient affects the attack process in the adversary training. And for this result, we can basically say that the robustness get boosted by 1.3. That suggests with smooth gradient, we can generate stronger adversary examples. That's why our adversary training get better results. And the next step 2 is that we just want to use ReLU with smooth gradient when updating network parameters. That means we get the network, we send to the network, we get the attacker, we send to the, we attack the network, and we get an adversary image. Here we use the original ReLU. And then with this generate adversary images, we send to the network for updating network parameters. But here we use the ReLU with a smooth gradient. And by doing so, we can see the robustness basically can be boosted by 2.8. So that can kind of suggest by using ReLU with a smooth gradient, can kind of find the better network parameter update directions to get better robustness. And of course, the third step that we can do is that we use ReLU with smooth gradient in both attacker and updated network parameters, right? So we get the attacker attacks the network and uses ReLU with a smoother gradient. And then when do the updated network parameters, we also use this one. And basically we can say the robustness can be boosted by 3.9, which suggests that the effects of using smooth ReLU with a smooth gradient in both attack and the updated network parameters are kind of works for different purpose, and by adding them together, you can get better results. And do remember that in this step, we forward we use ReLU, right, and we backward we use soft plus. That can kind of still leading some discrepancy, because basically in the forward path and the backward path, you are using very different actuation functions, right? So what we do next is we basically just use both exclusive use the soft plus. That means the forward is soft plus, backward is also soft plus. We will use this one to do the adversary training. And for this one, we can get robustness be improved by 7%. That's for Solve Plus. And also we generalize this to other actuation functions with those continuous gradient. You can see that we use CLU, GLU, ELU, and some of our own design called smooth ReLU functions. All of them, like say, the forward is continuous, and also the first derivative is continuous, right? And for all these actuation functions, you can say compared to the ReLU baseline, this at least can improve the robustness by 7%. This result can kind of suggest that all smooth actuation functions can substantially boost the adversarial robustness. And here are some visualizations. So compared to the ReLU, you can see the right one is CLU, which is a smooth actuation function. You can see the curve here is much more smooth compared to this, right? So this visualization can kind of qualitatively evident that the smooth actuation function can help the network learn some smooth loss landscapes, therefore get better adversarial robustness. The third work in this direction is that because in first two, we just talk about there's the convolution networks, we add some denoising layers, we manipulate its actuation functions, right? And this can kind of say, for third work in this direction, we just take a closer look at the recently emerged vision transformer, which is quite different from the convolutional network, right? And we just can do some very comprehensive and systematically evaluations to benchmark, say, whether transformers are more robust than CNNs or CNNs are more robust than transformers. So for the basic setting here, for the network selection, for CNN, we choose the very popular ResNet 50 as a backbone. And for transformer, we choose the DITS. So the DITS, compared to the original vision transformer, is that in this work, these authors just find that by adding some strong regularizations, like the data augmentation or some regularization on the network training, like the drop pass, they added this regularization to the training of vision transformers. They can kind of train very strong vision transformers by exclusively using the data from ImageNet. Otherwise, as shown in the original vision transformer, they need to pre-train on the huge GFT data sets or pre-train on the ImageNet 21K, then model can get good results. But here, the DITS just say with the strong augmentations, we can just use ImageNet to get a good performance. And the reason for choosing the ResNet 50 over the DITS is that first, in terms of the number of parameters, they're pretty close, 25 million versus 22 millions. And also regarding the top line accuracy, you find that these two models again reach pretty similar image accuracy. And here you will find that the transformer performance compared to the performance reported in their original paper, there's some difference. The main reason is that we just here train the transformer for 300 epochs. Oh, sorry, for 100 epochs. Our original paper trained for 300 epochs. Because that 100 epoch training is quite standard for CNN, and we just want to make sure both networks are trained for the same. And in our paper, we also do some additional ablations to train both models for 300 epochs, and everything we talk next basically just hold. So this is not a major concern. And in terms of the adversarial robustness, by evaluating these two models against the PGD 100, you will find that ResNet is much fragile than the DITS. Basically, the 32.3 versus 32.3. So by giving this result, we probably will say, okay, vision transformers in terms of adversarial buses, they are much more better. But when talking about the architectural comparisons between vision transformers and the CNNs, you will find that for CNN, like ResNet 50, by default, we use ReLU, right? But for the vision transformer, the default activation function is GILU. And this can kind of remind us that this difference between the activation function, just as we introduced in the smooth activation function paper, maybe the activation function design is the key to lead this performance difference. So by building upon these original results, the ReLU one, like say ResNet plus ReLU, will additional train ResNet with GILU. And we surprisingly find that basically now the vision transformer and the ResNet, basically they have the same performance. And also we evaluate these models against the auto attack, which is quite a very popular parameter-free attack evaluation suite for assessing the performance. And we find basically these two models still behave pretty similar. So in terms of the adversarial robustness, we can kind of conclude that vision transformers and the convolution networks, they are on par with each other in terms of adversarial robustness. And the next thing we look at is the robustness of out of distribution samples. So basically we consider 3 out of distribution benchmarks here. The first data set we consider is ImageC, basically less are image-like images plus some common corruptions like Gaussian noise, snow effects, or some other like pretty common corruptions. The second data set we consider is called ImageNet-A, basically less are a collection of real-world images, but much harder than ImageNet. For example, the true label of this one is bird. And you can see that the object rather than the vanilla images, the object here is quite small, right? So that's pretty hard to recognize even for our human. And the third data set we consider is called stylized ImageNet. Basically lets the ImageNet images go through some style transformations, which remove their original texture patterns, but only keep the shape patterns after this style transfer. So by looking at these 2 models on these 3 data sets, we basically find that DEITS behaves much more robust than the ResNet. So for example, on ImageNet-C, it can basically reduce the error rate by 4.3, and on ImageNet-A, it can increase the accuracy by 5.9, and on stylized ImageNet, it can improve the accuracy by 2.2. So both these improvements are pretty substantial. And we also tried, like in the first part, when evaluating the adversarial robustness, we also try to say align their activation functions, or align their data computation strategies, and we try to align the optimizers. Basically, we made a lot of efforts here. But we still find that vision transformer is much more robust than the CNNs. And to further align the discrepancy or the difference in their training techniques, we use knowledge distillation to recompare the performance between the vision transformer and the CNNs. So first, let's say we use vision transformer as a teacher model, and we use CNN as a student model. And here are the results. So first, like say on the ImageNet, you will find that the teacher and student basically they get similar results. So that's kind of what we expect, right? But on the auto distribution benchmarks, you will find that even the teacher is DEITS, the student ResNet 50 still fail to have the ability to generalize strongly on this, like say ImageC, ImageA, and stylized ImageNet. And then we do another experiment. We change, say, the teacher model be the CNN and the student model be the VIT. And here's the results. First, again, like for image performance, they're pretty close. That's within our expectation. And then for the auto distribution benchmarks, you will find that even if you use teach the ResNet or CNN as a teacher, which is pretty weak on this benchmarks, the student model can still substantially get some substantial improvements. For example, the improvement on ImageC is 6.4, and the improvement on ImageA is 6.5, and the improvement on the stylized image is 3.7, right? All these improvements are quite substantial. And this result basically can kind of further get conjecture that the key difference between the auto distribution robustness between the scene and the transformers is not lie at the difference of the training techniques, but rather maybe the architecture difference are the key reason that leading to this difference. So next, what we do is that we get the ResNet model, we get the vision transformer model, and we then create some hybrid model. That means it take partial of the ResNet and take another partial of the vision transformer, and then just combine them together, which is shown in this yellow bar. And compared to the ResNet, you can see this yellow bar basically can get a better result on image A and a better result on stylized image, right? But compared to the pure transformer architecture, you can see this performance is still lower. So this comparison, pretty initial like experiment here, can kind of suggest that transformer block is the key to get better performance on out of distribution robustness. So a summarization on this part is that basically we show that there are indeed some architectures can have better robustness in either adversarial robustness or out of distribution robustness. For example, we show that adding the denoising operations helps. We show change to the smooth activation function helps. And also we show vision transformers probably like they're inherently more robust than the original same designs. And I believe there should be much more works could be done along this direction to find the networks with better robustness. So the second part basically all treats, like say, adversary example as threats to the deep networks. And all we want to do is that we want to increase the robustness of the network and to defend against. So in this part, we take another direction to think of this question. We want to say, can adversary examples can bring some special or very, like say, particular regularization powers to regularize the training of the network, therefore can help them do better on recognition tasks. So basically, the third power called robust learning actually can improve generalization. And before our work, there are a lot of works qualitatively show that adversary example indeed can provide valuable and new features. For example, they do the visualization of loss gradient with respect to the input pixels of vanilla trained models and adversarial trained models. So look at the second row here. If we just do this visualization for the vanilla trained models, the visualization is quite noisy and there is no special patterns that we can catch, right? But for this third row here, you can see the for the adversarial trained models, the visualization can actually emerge with some very special patterns that can be recognizable by our human, right? So that kind of can suggest those adversarial trained models, their features are more human aligned. And also in or 2019 work, they show that with adversarial trained models, they are particularly good at tackle image synthesis task. But meanwhile, there are some dilemma that if you train with adversarial examples exclusively, you will lose performance on the standard benchmarks. For example, this blue bar is the model trained with clean images, and this gray bar is the model trained exclusively with adversarial images. And B3 and B7 are just two types of models, which I will introduce later. So basically, what you need to know now is that B3 is a small model and B7 is a large model. And y-axis is the top one accuracy on the ImageNet. So, but comparing this to, like say, different type of training methods, you can see that train exclusively on adversarial examples can significantly decrease the performance on ImageNet, right? Or on the evaluation of clean images. And we conjecture this performance degradation is that because adversarial examples and clean images, they have very different distributions. So train on clean ones or train on adversarial examples cannot generate pretty good on the clean images. So to validate this hypothesis, we take a very simple step next. We take these adversarial trained models, and then we fine-tuning them with clean images, which is shown in this orange bar. You can see this simple fine-tuning can significantly boost the performance of these adversarial trained models. For example, for B3 model, you can improve performance by around 3%, and for this B7 model, you can improve the performance by more than 1%. And by even look at this orange bar and the blue bar, you can surprisingly find that this one sometimes for these larger models can even outperform the standard training. They say first for pre-train on the adversarial images and then fine-tune on the clean images, they do much better. And these simple things can work like say great, and this can basically motivate us next to explore. Can we design some more well-designed things to get more substantial improvements? So let's lead to our solution called joint training, but with distinction. The joint training basically refers to that. First, for the original approach is that we first train with adversarial images, and then we fine-tune with clean images. And this thing can kind of may introduce the catastrophic forgetting issue, because you are fine-tuning your adversarial training models with clean images, and this can lose some important information that you learn adversarially, right? So to overcome this issue, what we do next is we then, rather than say do this first pre-train then fine-tune procedure, we just say we train with adversarial images and clean images at the same time. For this joint training, it may introduce some issues. That's because this joint training, as we previously mentioned, we believe adversarial images and clean images, they came from different distributions, right? So one layer in the traditional network design is called batch normalization. Basically, its purpose is to say, take the input and do some normalization on these input features over the whole batch. And because when we do the joint training, we are kind of trained with a mixture of distributions, right? We train with a mixture of clean distributions and our reserved distributions. And if we just naively apply this batch normalization layer, that could cause some confusions, because you are then do a single normalization over a mixture of distributions. So that can kind of give you the wrong estimation of mean and variance of this input batch, right? So what we do next to fix this confusion is pretty easy. We just say, okay, for all other layers, you just keep the same. But when you pass your signal through the batch normalization layer, you need to do some disentanglements. The first is that for the clean images, you just go through the original BN batch normalization layer. And for the adversarial images, you should specifically assign an auxiliary batch normalization layer to allow the adversarial signal to pass through. So as shown in this simple illustration here, by doing so can kind of ensure the adversarial images and the clean images, they estimate their mean and variance in a separate way, right? Therefore can kind of avoid the confusion between adversarial distributions and clean distributions. And we name our method as adversarial propagation because we, in the normalization layer, we do a very special handling the clean signal and adversarial signal. And for this auxiliary BN, we just threw it at the testing stage, and we only use the main BN for the inference for all the evaluations. So next, before we go to the main results, we will give our brief introduction of the backbone we use here. So before the backbone lab called EfficientNet, people already know that for a base network, if we make the network wider, or make the network deeper, or make the input with a larger resolution, people know that these 3 different ways do like separately, you can get better results. And EfficientNet just say, okay, if you already know these 3 scaling factors matters, so why not just do all these 3 at the same time? That means you want a larger resolution of the inputs. You also want the network to be deeper, but meanwhile, you also want the network to be wider. And they all apply the neural architecture search this type of techniques to search for the optimal values for scaling the image resolution, depth, and the width of the networks. And they call it as compound scaling. And by looking at the original EfficientNet results, you can see they achieve pretty strong results on the image classification task on all computational regimes. The x-axis basically indicate the computational budgets of different models. So B0 here, you can see pretty small computations, and that means this is probably our network is suitable to run on your mobile phones. And B7 here, you can see has a lot of flops here, basically indicate that's a very heavy model. And the y-axis basically is the ImageNet top-on accuracy. And especially for this B7 model, it is a performance of 84.5 top-on accuracy, is previous state of art on ImageNet classification task. And by building upon this very strong EfficientNet family, we get our ADU prop, which is shown in this red curve. You can see for all models, it can lead to some very strong improvements. And even for this previous state-of-art model, 84.5 results, we can further improve it by 0.3%, lead to the result of 85.2 top-on accuracy. And next, we evaluated these image trained models on the auto distribution benchmarks. We again the same here. We evaluated on the ImageC, ImageA, and select ImageNet. And here is the original EfficientNet B7 results. And you can see by apply on this auto distribution benchmarks compared to the original EfficientNet B7, which got 84.5 top-on accuracy on ImageNet, the performance here is much lower, right? So kind of suggests these benchmarks are extremely non-trivial to recognize. And you can see by adding the ADU prop, you can improve the performance by 5.1 on ImageC, 7% on ImageA, and 4.8 on stylizing. And in terms of absolute value, you can see that the ResNet 50 do pretty bad on these 3 benchmarks. Only 40.7 on the ImageC, while now we can get 85.2, right? And on ImageNet, its original ResNet can only got 3.1, where we can get 44.7. And on stylized ImageNet, the original one can only get 80%, but we can get 26.6%. So in terms of this absolute value, this ADU Pro can basically establish a very strong baseline on this auto distribution benchmarks. And then the next we compare to our result to the previous scale-up on ImageNet classification. That model basically trained by Facebook on billions of Instagram images. So compared to that Facebook baseline, first, in terms of the number of parameters, we are 10 times smaller, but this should be mainly attributed to the compound scaling design policy of EfficientNet. And then we're only trained on ImageNet, where for that Facebook model, it trains on billions of Instagram images. So that's 3,000 times more than ours. But in terms of the accuracy, you can see our space can still be 0.1 better than this Facebook model. So takeaways, the first is that adversarial learning features are indeed pretty valuable. And previous work showed that qualitatively, these features are human aligned, they can do pretty good. Like say, their feature space are more aligned with the human perception. But in this work, we're the first one quantitatively show that by using adversarial training features, we can get, like say, state-of-the-art accuracy on ImageNet. And also, adversarial example can be a pretty general way to do data augmentation. For example, like flipping, image flipping, we use it very frequently, or basically we can still use it everywhere when we do the image recognition task, right? When we train the recognition models. But flipping does not make sense to say for NLP or for reinforcement learning. So that's not a universal way to augment our data. But adversarial examples are kind of different. We can use adversarial examples to, let's say, for the image recognition. We can also get adversarial examples for NLP and even for the reinforcement learning. And therefore, like adversarial example can provide a very general way and where to regularize the model training. And the third is that this intelligent learning is pretty important, especially when the inputs came from different distributions. And as we show here, like say, we use ADU prop like 2 billion skin. We basically get the ADU prop, we show better performance on the image classification task. And recently, we also get one paper published in the iClear 2022 called Faster ADU prop, because the original ADU prop involves adversarial training and involves some like say very computational expensive operations. So basically, this fast ADU prop just show that we can train as cheaply as the standard when in a training setting, but still get better performance and better robustness. Also, we generalize this ADU prop work to the detection task, and we show that we use adversarial examples can basically get you much more robust object detectors. And also, we generalize this beyond the adversarial perturbations. Basically, we show that with the style transformed images like this one. This is an image with cat shape but with elephant texture, right? And this, of course, but even by looking at our human eyes, we know this images is very different from the standard image, right? So we should take care of the desynchrony learning part. And we show that by training with such images and do proper disentanglements, this can allow us to get a better performance on ImageNet and also better performance on a lot of auto distribution benchmarks. And also it can help us on the segmentation task. So all this work can kind of motivate us to further think, say, when training with synthetic data, which is quite different from the standard data, right? And also maybe the uncurated internet data, we should to take care about the disentangled learning part. And also for different applications like feature learning and supervised, semi-supervised setting or multimodal learning, we should all need to care about this internal learning. And lastly, I want to acknowledge my collaborators and also acknowledge to my sponsors. So basically, that's all for my talk, and I'm happy to take any questions.
Hi, so I think there's a question in chat box.
Okay, let me look at it.
Yeah.
Okay. It seems when there is no attack, the improvement is less comparing when there is attack in the denoising work. Yes, so in terms of like when you add in the feature denoising, you can see for the clean images, basically we expect the feature map to be pretty clean, right? So denoising will play little roles here. So the improvement is not huge, so that's something expected, right? But for the adversary things, that's a completely different story because they have noisy feature maps and denoising should be pretty effective there, so they can get large improvements. So I think that kind of makes sense for the denoising works, right? And also, this can kind of much more evident that because usually, like say, for model with better accuracy, you should expect that they should, when do the adversarial training, they should get better robustness, right? A more surprising part will be, okay, this two model has similar accuracy, clean accuracy, but their robustness are much more different. So that will be a very interesting point to look at, right? So I think denoising can kind of prove that even the networks share similar clean accuracy, but by looking at the robustness or some other metrics, they could be quite different. Okay. Any other questions?
And yeah. Any other question? Please feel free to ask here. So I basically have a quite general questions in our talk. What do you think your EDV prop can be used some which areas would you think maybe in general in the adversarial training be applied to more broader domain? Which kind of domain do you think can be applied to in the future
domain
perspective?
You refers to what?
A task, for example. The task.
Okay. So for EDV prop, like we already show on a list for like most mainstream recognition tasks like classification, detection, segmentation, they all works. And also maybe like something worth to try is that because the reason like you say pre-training is very popular, right? Probably like you say using EDV prop in the pre-training task, then you can get a very general robust descriptors of your features, and then by applying to a lot of different tasks, this much more robust or generalizable descriptors, feature descriptors can help you get better performance. So to be honest, I think there's no specific constraint on what domain or with which task EDV prop can be applied, because basically let's just let's say use the adversarial example to regularize the training, right? You should expect better results. As long as for a task you can find adversarial examples, EDV prop probably helps.
I see. Thank you for your answering. So all right. I think there's no further question coming up from our audience. Thanks again for your coming here to give us very great talk. We will be very grateful for it. When the situation is lifted, I guess it will end very soon for the COVID situation. Japan will open its border. We sincerely welcome you can visit us in our Nihonbashi office in the center of the Tokyo.
Okay, yeah.
We can come to see us.
Sure.
Thank you very much.
Okay.
Yeah.
Okay.
All right. Bye bye.
All right, see you guys.
This is the end of the
Bye.
talk. Bye bye.